All right, first things first, component vectors. We can separate any vector into, how much does it move horizontally and how much does it move vertically. So that's what this is. When you have a position vector where you have a number and then a 0, obviously this is going to be moving, horizontally and not vertically. So this would be how we could describe a vector horizontally, and this one vertically. Okay, so when they say, in this next example, find the component vectors, when we have a vector that has an initial 0.32 and a position, and a terminal 0.74, we're not even going to need the graph here. Okay, I'm going to first convert this to a position vector. So we have an initial point and a terminal point. Initial point is 3, 2. Terminal point is 7, 4. Okay, I'm going to slide it so that it starts at 0, 0. So I'm going to go left 3, down 2. If that point moves, this point has to also. Left 3, down 2. So that means we're starting at 0, 0 now, and we are ending, so I can use position vector brackets, right? We're ending at 4, 2, okay? Now, if you think about this 4, 1, 2, from the 0, 0 mark, there's my start. 2, 3, 4, 1, 2. There's my terminal. So this right here is the resulting position vector, right? Okay, that resulting position vector can be looked at as the sum of this one horizontally and this one vertically. Well, the horizontal one is 4, 0, and the vertical one is 0, 2. Now, 0, 2 we know is a position vector starting at 0, 0, but since vectors can be picked up and placed anywhere, I can take this vector, slide it on over, and just know that it is a vertical vector 2 units long. Okay? So these are the two components. All right, unit vectors. This is find the unit vector means it's 1 unit long. Okay, so I'm going to first graph this one, and then we're going to see how we can shrink it down. All right, so we'll have ourselves a x-axis here, a y-axis here. Okay, and we're going to go left 5, 1, 2, 3, 4, 5, and up 12, 1, 2, 3, 4, right here. Okay. This is the position vector that they're talking about. Okay, right here. Okay, now, what does this mean? Well, if I made a triangle out of this side of the triangle is 5 units long, yes, in the negative direction, right? This side of the triangle is 12 units long. If I use Pythagorean theorem, I will find that the hypotenuse, or in other words, the actual vector, right? This was the actual vector, is 13 units long. Okay, Pythagorean theorem found that. Now, the red that I have marked red is 13 units long. I don't want that 13 units long. I want to shrink it so that it's 1 unit long. So I'm going to zoom in and show you what I mean. I am going to multiply each side of this triangle by a scalar so that what I have is a unit vector 1 unit long. So I don't know where it goes, right about here somewhere. Okay, so this is how big it's going to be. So this would be my little triangle when I shrink it down, right? So in other words, to do that, I would have to shrink each side, or rather multiply each side by a factor of 1/13. So if we zoom into just this part, we multiplied by 1/13 to get this to be a 1 unit long. This side right here is 12/13, and this side right here is -5/13. Yeah? Okay. So 1 unit long. There it is. Okay. There's two special unit vectors that we like to work with a lot, and it is the I vector and the J vector. Okay. It didn't hint or tell us directly what I and J is, but I'm going to right here. Here it kind of hints at it, and here it kind of hints at it. Okay. But the I vector is a unit vector 1 unit long in a positive horizontal direction. So it is 1, 0. So 1 unit to the right horizontally. Okay. J vector is 0, 1, or 1 unit up vertically. Okay. So this red vector in the picture here is the sum of so many I vectors horizontally plus the sum of so many J vectors vertically. Okay, so let's look at the next example. Given this vector with an initial point P at 2, -6 and terminal point Q at -6, 6, write the vector in terms of I and J. So here it tells you subtract your x's and subtract your y's. How about we make it a position vector? Take the first point, the initial point, left 2, up 6. Left 2, up 6. That would make the initial point at 0, 0, excuse me, and the terminal point at -8, 12. Okay, so this vector is basically doing that, right? So what does this mean? How many horizontal vectors is it? Well, I is a single 1 unit vector that goes this way. Well, I need to make it negative then, because negative will make it go the opposite way. So we have -8 I vectors. And then how many vertical vectors? 12 little vertical vectors going up. That is this vector in terms of i's and j's. Okay, we're going to practice that again. Given the point at -1, 3 and a terminal point at 2, 7, what is the vector in terms of I and j? I'm going to change and have the initial point. I'm going to move the whole vector right 1 and down 3. Right 1 and down 3. So that means we're starting at 0, 0 and we are ending at 3, 4. Well, 3, 4 is something like that. So if we were going to break it up into a bunch of horizontals, we would say it is 3 I vectors and all these verticals, 4 J vectors. Done. Adding and subtracting vectors, these are more vector operations, and it's just piecewise. So you add vectors together, and i's are little vectors, so you add the i's with the i's, j's with the j's, right? So if they're saying find the sum, v1 plus v2, it's going to look like v1 plus v2. I don't really need the brackets. And I don't have any minus sign to distribute. If I was asked to subtract, then I would. And we end up with 6 i's when we're done and 2 j's. Okay, moving on. The next thing is talking about how, given information about vectors, we can come up with the vector in terms of i's and j's, okay? Now, here it says, write a vector with length 7 and at an angle of 135 in terms, write the vector. Oh, just write the vector. So it's, when we are asked to write the vector, we are asked to say, okay, well, how many i's are we talking about? And how many, let's start this over. When we are given things like the magnitude of the vector and the angle of the vector, we can generate what the vector is in terms of i's and j's. So when they say write the vector, how many i's, I'll call it x, and how many j's, we'll call it y. So we need to know what's the x and what's the y. Here's what we do know. We do know for this one, when we're at an angle of 135 and 7 units long, we're right here. Length is 7. Angle that put us over there is 135, okay? It is on your unit circle, okay? Well, what do I know about when this is on my unit circle? I'm going to zoom in. When this is on my unit circle, I am way right here, right? And when I am on my unit circle and I'm right there, the x is the cosine of theta, and the y is sine of theta. And if I'm making it so that the length isn't 1, but the length is 7 times larger, then that means that the x is going to be 7 times larger than what we would get with the cosine of theta. Excuse me, and my theta is 135 degrees. In my y, if it was a unit circle, the y value would be the sine of 135 degrees, but I'm stretching it 7 times larger. So the hypotenuse is 7 times larger, and the x's and the y's are 7 times larger, okay? Well, because I know my unit circle well, I know that this is going to be 7 times negative root 2 over 2. And the y value is going to be 7 times positive root 2 over 2. So in terms of i's and j's, I am going negative 7 halves root 2 for i's and 7 halves root 2j for my vertical. And that is this vector in terms of i's and j's. All right, dot product is next and very interesting. Okay, so looking at this next box of information here, this is your formula for dot product. Okay. Now, if you're trying to find the dot product of these two vectors, you multiply the two horizontal components together, A and C. You multiply the two vertical components together, B and D. And then you add those two products together. So you're going to take the sum of the products. Now, be careful. They have to be position vectors in order to do it. Okay, so next example here, we're going to find the dot product. So my dot product of V times W is it going to be the product of the horizontals plus the product of the verticals. There's my dot product. V times U. I wrote W, I meant U. Okay? That's it. All right. Find the dot product of these two. And just because it's I's and J's doesn't mean we have to do anything differently, okay? Because I's and J's, we might as well think of this as 5, 2, and this one as 3, 7, right? So first it says find the dot product. So V1, V2 is equal to 15 plus 14, right? The two horizontals multiplied, the two verticals multiplied, okay? Next, and this is a 29. Next, it says then find the angle between the two vectors. I'm going to go back to that box and point out that. This is how we're going to find the angle between two vectors. Okay, this is our formula for finding it. The cosine of that angle is equal to the dot product of the two vectors divided by the magnitude of the two vectors. Dot product of the two vectors divided by the magnitude of the two vectors. Well, let's find the magnitude. What's the magnitude of V1? Remember, a squared plus b squared equals c squared, right? So 25 plus 4, this is going to be the square root of 29. The magnitude of the second vector is a squared plus b squared equals c squared, right? 9 and 49. So the magnitude is the square root of 58. Okay. And I'll have to find the product of those two, 29 and 58, because my next step is the formula. The cosine of the angle is equal to the dot product divided by the two magnitudes, which is the square root of 29 times the square root of 58. Which is 1,682. All right. Well, I'm going to do inverse cosine. And I will get an angle of 45 degrees. Now, what does this look like graphically? There you go. So those are the two vectors. I'm not adding the two vectors together. I'm trying to find the angle in between them. So when I'm finding the angle in between them, they have the same initial point. There's my angle. There's my 45 degrees. And it looks pretty close to that. All right. Find the angle in between these two. Dot product. This would be a good one to pause the video, try on your own, and see if we agree, okay? I'm going to kind of go through it a little bit fast because I want to get to the application problem. Cosine of theta is going to be equal to the dot product, which is negative 15 and 48. Hey, I know that. We did that one already. That's a 33. The bottom is the magnitude of each one. The magnitude of u, Pythagorean theorem, produces a 5. Magnitude of v, Pythagorean theorem, produces a 13. I'm not going to show all my work for that. Please pause and do that. So that means that this is 33 over 65. If the cosine of theta is 33 over 65, do inverse cosine on each side, and we will get 59.49 degrees. Okay? So even though one of our vectors goes into quadrant 2, the angle will come out the way it should. 1, 2, 3, 4, 5. Of course I went off, because why wouldn't I? Right there is v, and u was negative 3, 1, 2, 3, up 4. 1, 2, 3, 4. Right there. And this angle then, in between them, is 59.49 degrees. All right. An airplane is flying at an airspeed of 200 miles per hour and headed southeast at a bearing of 140 degrees. A north wind, so the red is the bearing that the plane is trying to fly. Okay, plane is going red. A north wind from north to south is blowing at 16.2 miles per hour. That is this vector right here. Okay, so these are velocity vectors. Vectors can represent velocity or force. And in this case, velocity. So we have a velocity of the plane in the air, which is the red, and we have the velocity of the wind, which is the blue one. So the actual path of the plane is the sum of the red and the blue together. Okay? Well, red and blue make purple, not green, but you get the idea. Okay, so we're looking at, it makes the green vector. So what is the length of the green vector? Because that would represent the velocity. And what is the direction in which it is going? And I will tell you right now that I do not need to use the dot product. I just need to do law of cosines and law of sines. And here's what I mean. So we have our triangle. And if you look at that triangle, we can see that this picture might not be the best picture. Let's see if I can draw it better. And it'll be disproportionate, okay? Plane is trying to go this way. Wind is pushing it this way. Okay, the length of this is 200 because that's the plane's motor pushing it 200 miles an hour. But the wind is blowing it, so this one has a length of 16.2 miles per hour of the wind blowing straight south. Now, the actual path of the plane is going to be from here to here, right? And I don't really mean path. I mean that is the velocity that the plane is going. So this length, x, is the actual speed of the plane, okay? Now, I'm going to do one more thing. And on the graph above, they had a vertical axis drawn. So if I have that vertical axis here, this angle is 140. If I have that vertical axis here, in your high school geometry class, you learn that alternate interior angles, when you have two parallel lines, here's this one and this one are parallel. Two parallel lines cut by a transversal, alternate interior angles are going to be the same. So this one we know is 140, so that means inside the triangle we know it's 140, which is right here. I can do law of cosines. So review your law of cosines, and law of cosines is, in this case, x squared equals a squared plus b squared minus 2a b cosine of angle x, right? The angle, not the side length. Well, we know it's 140. So the side length squared is equal to 200 squared plus 16.2 squared minus 2 times 200, 16.2. Cosine of the angle across from the x is 140 degrees. X squared will be 45,226.40799. Square root, length x is 212.665, and that is miles per hour. Now, plane's trying to go 200, wind is pushing it a little bit, so it's going to go a little faster. Totally makes sense to me. Okay? The next thing is, what is the angle? Right? What's the bearing is saying, hey, what's the angle? So I need to find what they have labeled as alpha. See if you can see that. See the angle alpha there? That's the angle I'm trying to find. Again, I'm not going to do dot product. I don't need to. I can use law of sines. So I can say sine of angle alpha corresponds to its opposite side, 16.2, the same way that the sine of 140 degrees corresponds to 212.66. I'm going to take all the digits, 50136, so that I have accurate answer in the end. Sine of alpha is equal to 0.048965. Alpha is equal to 2.8066. Now, what does this mean? This is the angle of alpha. So the plane is actually going in, plane's bearing 142.8 degrees southeast.